Okay, greetings. Welcome everyone. This is week 12, and today we'll be discussing lead compensators. So, we have a couple of questions on them, which we'll discuss, and then this will be the final week for this tutorial session. So, in the first question, we have been given that a plant whose transfer function is given by this is desired that a lead compensator is to be is used to design unity negative feedback closed loop system with this plant. So the P of S is 1 or S in bracket S plus 2, and we have to design a lead compensator. So here the maximum phase lead that is phi m is 45 degrees, and this maximum phase lead angle uh, should be provided at a frequency of 8 radian per second. We have to determine T and alpha. So we know this. First, let's write down uh, the compensator as Kc into alpha in bracket Ts plus 1 over alpha Ts plus 1. So this is the transfer function of lead compensator. So since Pm has been given as 45 degrees, we can use this sin Pm is equals to 1 minus alpha over 1 plus alpha. This implies if I put 45 degrees here, this will be 1 over root 2, which is 0.707 equals to 1 minus alpha over 1 plus alpha. So if we cross multiply and solve, this results into alpha is equals to 0.172. So we have found alpha. We have to find the T. So we want this omega m to be 8 radian per second. The relation between omega m and alpha and T is given like this, under 1 over under root of alpha into T. So since we have already calculated alpha, we can substitute alpha here and substitute omega here to obtain T equals to 1 over under root alpha into omega m. So when we substitute alpha as 0.172 and omega m as 8 radian per second, the value comes out to be 0.3. So now we have three important things or three parameters here, that is Kc, alpha and T. We have found alpha and we have found T. If we get the value for Kc, then we have the complete idea of the transfer function. In the second part, it is desired that the static velocity error constant be 5 second inverse. Then we using this information we can find the value for Kc. So let us consider G of S to be C of S into P of S, and yeah, this would be Kc into alpha in bracket Ts plus 1 over alpha Ts plus 1 into P of S was 1 over S in bracket S plus 2. We will also take H of S to be 1. So, the static velocity error constant say KVE is given by limit S tending to 0 Kc into alpha in bracket Ts plus 1 over alpha Ts plus 1 into 1 over S plus 2 and S. So this is essentially we are applying final value theorem, sorry, initial value theorem. Oh, just hold on. Yeah, we are applying the initial value theorem. Man, sorry. Yeah, we are applying final value theorem. S tends to 0. So on the open loop transfer function, that is g of s into p of s into h of s, where h of s is 1. At this, we desire it to be 5. So after cancelling the s term here, yeah, and substituting the value for alpha and value for t, we get if we substitute value for t, we will get kc into alpha over 2 is equals to 5. This implies after substituting alpha equals to 0.172, we will get Kc to be 10 over alpha, which is 58.1. Alright, so now we have found out Kc, we have found out alpha, and we have also found out T. So that completely describes the controller C of S. Now we have been asked to determine the low frequency magnitude in decibels of this compensator's frequency response transfer function. So the third part asks for low frequency magnitude. So we can write the sinusoidal transfer function by substituting s equals to j omega. It is given by kc into alpha in bracket t into j omega plus 1 over alpha t omega, alpha t into j omega plus 1. Alright, so we have been asked at low frequencies. So that means omega tending to 0. So here there is no issue, like no indeterminate quantity if omega tends to 0. So limit omega tending to 0 c of j omega would be kc into alpha. In the numerator omega is 0, so in this bracket there will be 1, and denominator also when omega is 0 we will be left with 1. Okay, so Mm, just 1 second. Yeah. So if we get the value for Kc into alpha, which was from here, is 10. So if we take it into decibels, log 10 base 10 is 1, so 20. So we have found the low frequency magnitude. So that ends about the first question. Now coming to the second question, a lead compensator introduces an open loop 0 at -2. So we have, okay, and an open loop pole at 20. So for a lead compensator, so pole is at um, -1 over alpha into t, and 0 is at -1 over t. So the 0 is given at -2 and the pole is given at uh, yeah, pole is given at -20. So from here we can solve that this would get cancelled, the minus sign would get cancelled, and this would result into t equals to 1 by 2 or 0.5. So substituting here, the minus sign would again get cancelled. Alpha would become 1 over t into 20. So half into 20, that is 1 over 10. So this would be 0.1. Alright, so uh, here also we have found the two components for the lead compensator. Now we have been asked to determine corner frequencies in radian per second of the compensator's sinusoidal transfer function. So let's just write C of S first. Kc into 0.1 in bracket 0.5 Ts plus 1, and alpha into Ts would be 1 by 20. So yeah, 0.05 into S plus 1. So now we have been asked the corner frequencies. Mm. So if we look at the denominator, we will get 1 over t, that is one corner frequency, which turns out to be 2 radian per second, and another corner frequency would be 1 over alpha t. Yeah, 1 over alpha t coming from the denominator. This would turn out to be 20 radian per second. So these are the corner frequencies in radian per second. Now we have to find the maximum phase lead in the degrees provided by the lead compensator. So maximum phase lead, which is Pm. So sine of Pm is 1 minus alpha over 1 plus alpha. So if we substitute value of alpha, sine Pm would be 1 minus 0.1 and 1 over 1 plus 0.1. So this will be 0.9 by 1.1. This implies Pm is sine inverse of 54.9 degrees. So we have found the maximum phase lead in which is provided by this lead compensator. Now we have been asked the frequency in radian per second at which maximum phase lead would be provided. So it is given by omega m, which is 1 over under root alpha into t. So if we substitute for alpha and values of t, this turns out to be 6.32 radian per second. Now in the fourth part, we have to find the value of parameter Kc, so that the low frequency magnitude value in decibels of the compensator's sinusoidal transfer function turns out to be 0 decibels. So if it is 0 decibels, let's change the color. So this implies what? Okay, if say we have 0 dB, this implies log base 10 and whatever was this is 0. So when would the log be 0? Sorry, yeah, the log function will be 0 when x is equals to, the log function would be 0 when x is equals to 1. So that means when we take the limit, the value should equal 0. So we did this in the previous question as well for the low frequency magnitude. Since the transfer function form remains the same, it is a lead compensator. This limit turns out to be Kc into alpha. So essentially 20 log base 10 Kc into alpha is 0 dB. This implies Kc into alpha is 1. And since alpha is equals to 0.1, Kc would become 10. So here also, using the specifications uh, given by the the pole, the 0, and the value of Kc, we are able to determine or we are able to design this lead compensator Cs. So now there are three statements made in the question, and we have to determine whether they are true or false. So coming to the first part, a lead compensator improves the transient response and amplifies high frequency signal. So this statement is true. Let's look at a body plot of a lead compensator. This is omega and this is C of j omega's magnitude. So at low frequencies, we don't see anything. In between the 2 points that is given by hello. Hello, Anil, can you mute your microphone, please? All right, so great. Yeah, coming back to the body plot of the lead compensator, nothing happens to the low frequencies, and at the high frequencies, we get higher gain. So higher gain at high frequency. So yeah, the lead compensator amplifies the high frequency, and it also improves the transient response as it adds a phase lead to the output of the system. Right. So because of the added phase lead, uh, the if we draw the response of the output of the system, it would appear to be faster. Now coming to the second part, a lag compensator increases the system bandwidth. This statement is false because if we draw the phase diagram, so if the blue one happens to be the original one, uh, then then this would be compensated. So the crossover frequencies get shifted towards the lower side, and hence we would look at yeah hence the system bandwidth would decrease, not increase. So and coming to the third part, a typical lead lag compensator for a typical lead lag compensator, the high frequency components are attenuated. So again, if we were to draw the body plot for specifically the magnitude plot, magnitude versus omega, the low frequency components looks like this. This is the portion of lag compensator, and this is the portion of lead compensator. So for a typical lead lag compensator, the high frequency components are attenuated. No, they are not. They are uh, held almost the same as low frequency component. So what happens here is, if I were to denote, let me increase the thickness over here. Yeah, if I were to denote a lag compensator like this, okay, and a lead compensator, say like this, then the addition of these two would be this. Then we are shifting down, holding it the same, coming up, sorry, and stabling here. So we can see that the portion of the compensator where, so the lead compensator is here, the lag compensator is here, the high frequency portion, uh, so when the input is having high frequency, both the lead compensator and the lag compensator would cancel out each other's response, and there will be neither any attenuation nor any amplification. So a typical lead lag, for a typical lead lag compensator, the high frequencies component are not attenuated. So this is false. All right. So do we have any questions here before we can move on to some next part? Okay. So all right. So we have some time left. Let's take a look at a different concept today. Let me try it one last time. All right. So we will discuss a modern control technique called model predictive control. With a simple example. Here the idea is to use a model of the system so that we can predict into the future uh, what control input would result in what kind of behavior, and then we trace back and solve for those control inputs, which essentially would end up giving us say the output which we desire. Okay, so let's start with the model. Xk plus 1 equals to Axk plus Buk and y of k equals to c into x of k. So let us assign certain values to a. Let's call this as 0.9, b as 1, and c equals to 1, just for simplicity in calculation. So we discussed for two important things here. First is control horizon, and second is prediction horizon. So you start at any given time k, you will be looking some steps into the future. You will be projecting into the future using the model. So up to the time till which you are going to predict is called prediction horizon, and to reach that predicted value up to the time uh, till which you will be looking ahead into the future is called control horizon. So let us pick our control horizon to be 2, say NC to be 2 and NP to be 3. So what we will say is I am here standing at time k, and this is value of my output y. This is what I want it to be, okay, in future. So this is time k plus 1, k plus 2 and k plus 3. So this is where I had wanted it. So let me draw a line through this and call this y desired or y reference. So I am asking what should be my u values here. So, and whatever this value of u is, I am going to hold it. So u at k plus 1, and whatever it comes, I'll just hold it so that my y reaches where I wanted it to reach. Okay, so let us hypothetically say that y ref we have to reach 1, and x of 0 is 0. So if I were to write the predictions, so x1 would be a into x0, which is 0, plus b into, let's write it, x0 plus b into u0. So this is 0 plus b is 1, so u0. X of 2 would be a into x0 plus b into u1. Okay, so sorry, this would be x of 1 and b into u of 0. So what was x1? It was u0. So if we substitute it here, this would be a into u0 plus b into u1. So we know the values of a, which is 0.9, and b is 1, so u1. So now I am saying my control horizon was 2. That means I want to determine only two inputs, u0 and u1, and I am going to hold the same input for my third prediction, that is x3. So here you see, right, I am holding the input. So what is x2? x2 is this quantity. So this will be 0.9 into 0.9 u0 plus u1 plus b into u1. Okay, so x3 is written as 0.81 u0 plus 0.9 u1 and u1, so 1.9 u1. Okay, so here for each one of this we will use yk equals to ck, c into xk. C was 1, so y is x. So my y1, y0 is 0, y1 is u0 y2 is 0.9 u0 plus u1, and y3 is 0.81 u0 plus 1.9 u1. Okay, so now I have introduced to the idea of control horizon and prediction horizon. Now let's take a look at one more important idea, as which is of solving an optimization problem. To calculate control input. So what do I want to solve? I want to minimize. What do I want to minimize? The difference between where I am. Okay, say y1 minus yref whole square plus y2 minus yref whole square plus y3 minus yref whole square. I want to minimize this. So if I minimize these things, by that what am I trying to do? I am trying to take my y closer to yref. Okay, and to do that I will use, or I will change the values of u0 and u1. So I'm trying to find those values of u0 and u1 which will minimize this. So let me write it this way: find those values of u0 and u1 that would minimize. So what is this? This is a sum. Okay, it is sum of squares, and inside terms are is my prediction and my reference. So this is sum squared prediction error. Okay, so if I do this, I want to minimize this function. Let me write, substitute y1. So this is minus 1 whole square plus I have 0.9 u0 plus u1 minus 1 whole square plus 0.81 u0 plus 1.9 u1 minus 1 whole square. Alright, so how can we solve this? Let's call this objective as j. So we'll take partial derivatives dj by du0 and get it. So 2 will come forward, 2 in bracket u0 minus 1, and then derivative of u0 will be 1 plus 2 in bracket 0.9 u0 plus u1 minus 1 multiplied by 0.9 plus 2 in bracket into 0.81. So let's just clean this up a bit. We'll be equating this fellow to 0 because we are looking for a minimum value. So the derivative should be 0. This implies this 2 can be cancelled. Let's change the color. So 2 can be cancelled, and we'll take this together. So we have 1 here, then 0.9 into 0.9, 0.81 here, and then 0.81 into 0.81. Let's pull a calculator for that. Oh yeah, plus 0.6561. So let's stick to 0.66. Okay, into u0 plus, let's take the factors of u1. So here we have 0.9, then we have 1.9 into 0.81. So this will come out to be 1.54 into u1, and I'll take this minus 1 from here, minus 0.9 from here, and minus 0.81 from here, and send it on that side. So it will be 1 plus 0.81 plus 0.9, so 2.71. All right, so we have, if we add these, okay, 1 plus 0.81 plus 0.66, this is 2.47, plus 0.9 plus 1.54 would be 1 point, sorry, would be 1, would be 2.44. u1 is equals to 2.71. So we have gotten one equation in u1 and u2. If we get another equation in u1 and u2, we can hopefully solve for u1 and u2. Sorry, u0 and u1. So we take the derivative again. So first term's derivative is 0. There is no u1 term there. Second term is then the u1's coefficient is 1, so that would stay the way it is. Then we have 2 in bracket 0.81 u0 and this term will get multiplied by 1.9 equal to 0. So here also 2 and 2 would get cancelled, and if we combine the coefficients of u0, that is 0.9 plus 0.81, so that would be 1.71 into u0 plus, we have 1 here, and we have 1.9 into 1.9 here, that would be 3.61 into u1 is equal to, we have 1 here and 1.9 here, so that will be 2.9. So we have two expressions. This is the first one. So we have two equations, and we have two unknowns u0 and u1. We can solve for that. So yeah, let's so if I were to solve this, I would take the inverse of this matrix and solve for u0 and u1. So, all right, I'll just take a little bit of shortcut and use MATLAB to calculate this matrix inverse. So if I were to write this as A into U equals to B, my U would be A inverse B. Okay. Okay, finally it's up. So 1.71, 3.61, then we have 2.47, 2.44. So the inverse of this matrix is, okay, hmm. Okay, anyway, my computer decides to take its own time, so let it keep going. Meanwhile, I'll just recap the idea. The idea for model predictive control is to utilize uh, the notion of uh, utilize the model to perform predictions, and in doing those predictions we solve an optimization problem by essentially asking what are the control inputs which, if provided to the system, would result in desired output. Okay, so that is the question we are asking. So at each time instance we determine inputs up to control horizon, here too, so that the predictions done up to control up to prediction horizon results in the desired output. Okay, and minus 0.3604. So, my u0 and u1 comes out to be 0.5706 and 0.5330. So these are my u1, u0 and u1. So if my controller is correct, let's try to calculate my x1 now using this value of u0. So x1 was, this is what we solved, was u0 itself. So x1 would become 0.5706, and my x2, so what we generally do is we calculate inputs up to prediction horizon, sorry, control horizon, and implement the first input. Here, just for just for demonstration, I want to implement both the inputs. So u0 has been implemented, and now I have uh, x2 as 0.9 into x1 plus u1. So 0.9 into this would result 0.5706 5135 plus 0.5330. So, so if I were to implement these two control inputs, it will overshoot me a little bit above my desired value of 1. So y1 would be x1 and y2 would be 0465. So as you can see, by manually solving, we have reached a system of the form AU into B. So if you were to solve this entire optimization problem in matrix form, or express this entire optimization problem into matrix form, and take the matrix derivative and take the vector derivative and set it to 0, you will end up with this kind of form. So a linear system, something like this given here in state space form, along with a quadratic objective function like minimization of some squared error problem, would essentially result into a solution of the form u equals to A inverse B. That means if you already know your system, you can uh, you know pre-compute the coefficients of A and pre-compute its inverse, and in implementation you can just take the feedback, put it into that matrix B, the vector B, and multiply it with A inverse to obtain your control input. So for linear systems, this can be implemented pretty efficiently. So I think that's all for today. Thank you for joining for today's lecture and for all the lectures we have been discussing. I hope you enjoy doing controls in later point. Do we have any questions before we close? All right. I hope this was helpful. So, uh, yeah, Anil, any questions? So, all right. I think if there are no further questions, let's uh, wrap up. Good luck. Thank you.